Good day everyone! So today, here in Statics of Rigid Bodies, we are now going to discuss our 10th lesson, and that is Equilibrium of Non-Concurrent Force System. So for this topic, students must be able to compute reactions of supports of non-concurrent force system. So let us start our discussion. Before we proceed to our discussion, let us first have this pre-assessment. Okay, so for this pre-assessment, you have to determine the reactions at A, B, P, Q, C, and D from the following figures. So this is the first figure, the second figure, and the third figure. So what you're going to do here, you just have to comment your name, your section, and the answer. Okay, and you have to indicate what reactions you are answering, whether it's reaction A, reaction B, reaction P, reaction Q, reaction C, or reaction D. Okay, so you just have to comment it here in the comment section. So the first students, okay, who will give the correct answer, okay, will receive the bonus points. Okay, so maximum of 2 points for every student. Okay, I hope that you get this bonus points, class. So let's start our discussion now about equilibrium of non-concurrent force systems. So the conditions of equilibrium for a non-concurrent force systems are obtained by determining the equations that produce a zero resultant. So again, for a non-concurrent force system, okay, that is in equilibrium, okay, so we can use the following equation. So since the resultant is zero, okay, so the summation of forces horizontal, which is also equivalent to the horizontal component of the resultant, it will also be equal to zero. We can also use this equation, summation of forces vertical, which is equal to zero. This is summation of forces vertical. This is equivalent to the vertical component of the resultant. So since the resultant is zero, so the summation of forces vertical is also zero. And also, the summation of moment, okay, at any point in the system will also be equal to zero. So these are the equations that we can use in solving for non-concurrent force systems in equilibrium. So since we have here three equations, okay, that we can generate, so we can solve non-concurrent force systems that has or that have three unknown forces, no? So we can use these three equations to solve for those three unknowns. So let's start solving problems now about equilibrium of non-concurrent force systems. So for our first sample problem, so the truss shown is supported on rollers at A. So this is the roller at A and a hinge at B. So this is the hinge at B. So we have to solve for the components of the reaction. So take note here, okay, that we are asked here to solve for the components, okay, components of the reaction. So we have to give the horizontal and vertical component of the reaction. If it's if let's say if it's a hinge, no? So for hinge, we know that there's a horizontal and vertical component. So we have to show that in our answers, no, the components of that reactions, no. So from here, no, we can now start solving. Okay, so again, we are asked here to solve for the components of the reactions. Okay, so as we know, okay, that uh, for for roller at A, we know that its reaction is just a normal reaction, right? So we will name that normal reaction as RA. And as we know also that it is applied, okay, perpendicular to the surface where the roller is lying. Okay, so your RA will be um, applied somewhere here, no, at point A. So this will be the application of RA. And since our surface here is just horizontal, so RA will just be vertical. Since we have to apply RA perpendicular to the surface, no? Okay, so this will be our RA. So we are looking for this. We have to solve for RA. And now for our um, hinge at B, okay, so since we know that for hinges, okay, there will be one horizontal and one vertical reaction. So this will be the vertical and horizontal reaction, okay, provided by hinge, no, at B, and then we will name it as BV and BH. So these are the components, okay, of the reactions at B. So we have to show, no, in our final answers, the value for BV and BH, okay, and also for RA. So these are the unknown forces, okay, that we have to solve, okay, for this system, okay, or for this non-concurrent force system. Okay, so to solve first, no, for the let's say for the horizontal forces, no, so we can use summation of forces horizontal is equal to 0, and our assumption here is positive for forces directed to the right. Okay, so we can start our summation from here. So as we know, we have here BH. So BH is directed to the left. So it will be negative here. And we have here 240 pounds. And as we know, this is directed to the right. So it will be positive here. And this is equal to 0. Okay, so solving now for BH. Okay, so we can say that BH now is equal to 240 pounds. So as we can see here, only 240 pound and BH are the horizontal component, no, or the horizontal forces, okay, in this system, no. So if we have here an applied 240 pound horizontal force, of course, our horizontal reaction, so it should react, okay, opposite the direction of the applied horizontal force or horizontal load. So that's why our BH here should be directed to the left, okay? So that it will keep, okay, the equilibrium, okay, of this force system, okay, in terms of the horizontal forces, no? Okay, now, this is already an answer. So BH is equal to 240 pound. Now, we can also use summation of moment at B. So if we sum up moment at B, so BV and BH will be cancelled. It will not be included in our summation since it passes through the point where we are going to solve for moment, no? So BV and BH will be cancelled, and the only unknown here will be RA. So from here, from summation of moment at B is equal to 0, we can solve for RA since this will be the only unknown. So let's start summing up all the moments, okay, about point B. So we will start with RA. So for our RA, okay, so its moment about point B will be RA, okay, times its moment arm, which is 12 plus 12. So that will be 24. Okay, and its rotation, okay, about point B will be clockwise. Okay, that's why it will be positive here. Now, for 400-pound force here, okay, so its moment about point B will be 400 times its moment arm, which will be 12 plus 12 plus 12, so that will be 36, and its rotation about point B will be counterclockwise, so it will be negative here. Now, for 240-pound force, so its moment about point B will be 240 times 16. Okay, so its rotation about point B will be clockwise. That's why it will be positive here. Now, for 600-pound force, its moment about point B will be 600 times its moment arm, which will be 12 feet, no? So this is 12 feet, so that this will be 600 times 12. And its rotation about point B will be counterclockwise, so it will be negative here. And we will equate this to 0. Okay, so the only unknown here is RA. So solving for RA, okay, so we can transpose the other terms here, no, so that we can solve for RA. So we can transpose negative 436 to the other side, so it will be positive 400 times 36, and then we transpose positive 240 times 16, so it will be negative 240 times 16. Okay, and then we transpose 600 times 12, negative 600 times 12, so it will be positive 600 times 12. So from here, we will divide this by 24 to solve for the value of RA. So the value of RA is 740 pounds. So for RA, we are also solving for this, no? So we can now box this. Okay, now for the remaining unknown force, which is BV. Okay, so we can use the remaining summation of forces, which is summation of forces vertical, or we can also take moment, okay, about point A. Okay, so it depends on you, no? So again, you can use summation of forces vertical, or you can sum up moment at some other point. So since we already solve for the moment at B, so we can actually solve for the moment, okay, at A. Okay, so if we take moment at A, okay, so RA will be cancelled and BH will also be cancelled since it will pass through point A, and the only unknown will be BV, and from that we can solve for BV. But here we are going to use summation of forces vertical. No? So again, it depends on you. Okay, so you can choose, no, any equation here, no. Okay, so but here we are going to use summation of forces vertical. So for summation of forces vertical, we will just sum up all the vertical forces, okay, from this system. Okay, so we have here RA. So RA is upward, so it will be positive. And then we have here negative 400 since this is downward. And then negative 600 since it is downward. And we have here positive BV since it is upward. And we will equate this to 0. No? So we already solved for the value of RA. So we will just substitute RA here. Okay, so this will become 740 minus 400 minus 600 plus BV is equal to 0. Okay, so solving for BV, we will just transpose all this value. So this will become negative 740 plus 400, okay, plus 600. So that will be 260 pounds. So this will now be the answer for BV. No? So as you can see here, in this problem, no, we use three equations because we have three unknowns. So we use summation of forces horizontal, summation of moment at B, and summation of forces vertical. Okay, so let's proceed now to the next example. Okay. Okay, so for sample problem number 2, determine the load P required to hold bar AB in a horizontal position on the smooth incline shown below. Also, determine the reactions at A and B. So this will be our structure here. Okay, so this bar, no, this is bar AB. So this bar AB is supported, okay, by these inclines. Okay, so this incline is incline 60 degrees, no? So this is from the horizontal. This is 60 degrees from the horizontal. And here, this incline, this is 45 degrees from the horizontal. Okay, so what we're going to do here is solve for the load P. Okay, so this is the load P and the reactions at A and B. So as we know, since this is just a smooth surface, okay, so this is a smooth surface, so there will only be a normal force here at A and a normal force here at B. Okay, so let's start solving this. For P, the normal reaction at A, okay, so this will be our A, and B is here, so we will solve for the normal reaction at B. Okay, so we must first draw the free body diagram of the uh, bar, no? So this is bar AB. Okay, so this will be the free body diagram of bar AB. So here at A, so this is supported by this incline. So this surface, no, it will provide a normal reaction, no? And its point of application will be at the point of contact of the bar and this surface. So it will be somewhere here. And this normal force, okay, it will be applied 90 degrees or perpendicular, no, to this surface. So it will be applied this way, no. So if we are going to draw a vertical line here, okay, so if this surface is 60 degrees from the horizontal, okay, so its angle, so this angle, no, from the vertical, okay, from the angle of NA, okay, from this vertical line, okay, it will be 60 degrees as well. Okay, so we will name the normal reaction at A as NA. Okay. Also, for normal force or for surface B, no, so the reaction force here will be a normal force, and also it will be applied at the point of contact of this rod and this surface, no? So it will be here at this point. And this normal force, no, we will name it as NB, and this is applied, okay, perpendicular or 90 degrees, okay, from this incline. So if this incline is 45 degrees here, so if we draw a vertical line here, so the angle of this normal force, B, okay, so it will be 45 degrees from the vertical. Okay, so from here, we can now start solving. Okay, so the unknowns here are NA, P, and NB. So let's see the equations that we can generate from this. So for this, no, we can sum up moment at A. So summing up moment at A, okay, so NA will not be included. It will pass through A, so it will have no moment. So P, 400 pound, and NB will all have moment at A. So let's start summing up moment. So this will be equal to 0. Okay, so for P, okay, so its moment about point A will be P times 4. Okay, so, and its rotation about point A will be clockwise, so it will be positive here. Now, for this 400-pound load, okay, so its moment, okay, about point A will be 400 times its moment arm, which is 14 plus 4. So that will be 18. And its moment or rotation about point A will be clockwise as well. So it will be positive also here. Now, for NB, okay, so for NB, we can solve for its moment, okay, if we resolve first this NB into horizontal and vertical component. So for its horizontal component, no, it will have no moment about point A since it will pass through. It will pass through point A. Okay, while your vertical component here, the vertical component of NB, it will have a moment about point A. So its vertical component will be this side, no? So this will be cosine. We need cosine here since our angle is here, no? So adjacent over hypotenuse. Okay, so for the vertical component of NB, that will be NB cosine 45 degrees. Okay, and its moment arm, okay, about point A will be 2 plus 14 plus 4. So that will be 20. And its rotation about point A, the vertical component of NB, okay, so its rotation will be counterclockwise. So it will be negative here. And this will be equated to 0. So here, as we can see, we have here two unknowns, no? So we cannot solve for this, no? So we have to generate another equation. So we can sum up moment at B, okay, to generate another equation. So summing up moment at B, okay, so the equations that, or the forces, no, the forces that will have moment will be NA, P, and 400 pounds. So NB will have no moment since it will pass through point B. So for NA, only the vertical component of NA will have a moment about point B. Okay, since its horizontal component will be or will pass through point B. So the vertical component of NA will be NA cosine 60 degrees. Okay, since our angle is here, so the side that we need here is this adjacent side, no? So that will be the vertical component of NA. Okay, and its moment arm about point B will be 4 plus 14 plus 2. So that will be 20. Okay, and its rotation about point A will be clockwise, so it will be positive. Now for P, no, so for P, its moment about point B will be P times moment arm, which is 14 plus 2, that will be 16. And its rotation about point B will be counterclockwise, so it will be negative here. Now for the 400-pound force here, so okay, so its moment about point B will be 400 times 2. So its rotation about point B will be counterclockwise, so it will be negative here. And this will be equated to 0. So this will now be our equation 2. So as you can see here, we still have two unknowns here. So we cannot solve simultaneously equation 1 and equation 2 because here in equation 1 the unknowns are NB and P, while here in the second equation the unknowns are NA and P. So we cannot solve them simultaneously because we have three unknowns. So we have to generate one more equation. So we can use summation of forces horizontal, okay, to generate one more equation. Okay, so for summation of forces horizontal is equal to 0. Okay, so we can sum of forces horizontal, no? So for in this case, no, so only NA and NB will have a horizontal component, no? Okay, and that will be included in our summation for horizontal forces. For NA, its horizontal component will be NA sine 60 degrees. Okay, and it is positive since it is directed to the right. And for the horizontal component of NB, so it is directed to the left, so it will be negative here. Okay, and the horizontal component of NB will be NB sine 45 degrees. And this will be equal to 0. So this will now be our equation 3. Okay, so from our equation 3, okay, from these three equations rather, no, so we can solve for the three unknowns. Okay, so what we can do here is solve, so we can solve for NB, okay, from equation 1. Okay, so we can express NB in terms of P. Okay, so also from equation 2, we can solve for NA, okay, and express it in terms of P. Okay, so this is from equation 2. And this NB and A, we can substitute this to equation 3. Okay, so that when we substitute this NA to this and this NB to this, so the only unknown will just be P. Okay, so from that, now we can solve for P. So again, we will just substitute NA and NB from equations 1 and 2, okay, to the equation, to the third equation, which is this equation, no? Okay, so we just substitute them. So for NA, okay, this is P16 plus 400 times 2 over cosine 60 degrees times 20. So this is from from this equation, no? So don't forget this sine 60 here. So we still have sine 60 here minus NB. So our NB is P times 4 plus 400 times 18 over cosine 45 degrees times 20. So that is from equation 1. Okay, so times sine 45 degrees. So this will be equated to 0. So the only unknown here will be force P. So we can now solve for force P. So let's simplify this further. So P16 over cosine 60 degrees times 20 times sine 60 degrees, that will be 4 times square root of 3 over 5P. Okay, so we also have 400 times 2 over cosine 60 degrees times 20 times sine 60 degrees. So that will be 40 times square root of 3. And we have here negative, no, we have here negative. So P times 4 over cosine 45 degrees times 20 times sine 45 degrees. So that will be 1/5 P. So this is negative here since we have here negative. And also for 400 times 18 over cosine 45 degrees times 20 times sine 45 degrees. So that will be 360, and it is negative here, so it will be negative here. And this will be equal to 0. So we can combine P here, no? So this P and this P we can combine, and we can combine the constants. Okay, so from here, so this will now become negative 1 plus 4 times square root of 3 over 5P. So we already combined this P and this P. So equal to, so we transpose 360. So this is negative here, so it will be positive here. And we transpose this 40 times square root of 3, so it will be negative here. So solving for P here, okay, so again, this will just be 360 minus 40 times square root of 3 over negative 1 plus 4 negative 1 plus 4 square root of 3 over 5. Okay, so that will give you, what will be the answer? Okay, so that will give you 245.20 pounds. So that will be the value of P. So since we have already solved for P, we should, of course, we have also to solve NA, no, and NB. So we can solve NA and NB by using these equations. Okay, so we can substitute the P that we obtained here to this P, no? So solving for NA, we just substitute P here. So substituting P here, so that will be P, our P is 245, no? So we can, it's better if we input all the values of the P, no, that we obtain. So that will be P times 4, 16 rather. Okay, so let's repeat this. So again, that is P times 16. So we are solving for NA, no? Let's input this in our calculator. Plus 400 times 2 over cosine 60 degrees times 20. So the answer for this is 472.32 pound. Now for Na, so we will also substitute here the value of P here, no? So again, we will input all the decimal places, no, that we obtained here in force P. Okay, so P times 4 plus 400 times 18 over cosine 45 degrees times 20. So that will be 578.47 pounds. So this will now be the answers for this problem. This will be the values of P, NA, and NB. So this will now be the answers. Let's proceed now to sample problem number 3. So the forces acting on a 1-foot length of a dam are shown. So the upward ground reaction varies uniformly from an intensity of rho 1 pound per feet at A to rho 2 pound per feet at B. So find rho 1 and rho 2 and also the horizontal resistance or reaction to sliding. Okay, so this problem, no, we actually solved this in our topic about resultant, no, of non-concurrent force system. So here, this will now be considered, no, as a system, no, in equilibrium, as a non-concurrent force system in equilibrium, since we will solve for the ground reaction. Okay, so this dam, okay, this is supported, okay, of course, by this ground, no. So this serves as its support, no. So in the problem, it is mentioned, okay, that the reaction, okay, that this ground, okay, will provide to support this dam, okay, as it was mentioned here, the upward ground reaction. Okay, so as you can remember, and also as you can notice here in this system, no, or structure, no, we can analyze, okay, that its resultant will be downward to the right. Okay, since all of the vertical forces here are downward, no, and also for the horizontal force here, it is greater than this horizontal force, no. So we can simply say, no, that the resultant for this structure is downward to the right. Okay, so of course, the ground reaction, it should be for the upward for the vertical reaction, no. So for the vertical reaction of the ground, of course, it should be upward. Okay, and that upward ground reaction, as it was mentioned in this problem, it varies. Okay, it varies uniformly. Okay, so when you say that it varies uniformly, meaning to say, okay, our reaction here, okay, is a, let's say, trapezoidal reaction. Okay, so since the intensity here is from rho 1, okay, to rho 2, so this is not uniformly distributed. This is varying uniformly. So it can be either triangular or trapezoidal. But in this case, we have here an intensity rho 1 and intensity rho 2. So this is not intensity from 0, okay, to rho 1 or rho 2, okay, but this is from rho 1, okay, to rho 2. So we can say from here that that upward ground reaction is a trapezoid, no, is a trapezoid. Okay, and also, class, it is also mentioned here that we have to solve for the horizontal resistance or the horizontal reaction. So in this case, since we can see here that the horizontal the resultant, no, the horizontal component of the resultant, okay, it will be directed to the right plus, okay, it will be directed to the right. So the resistance here or the reaction, okay, it should oppose that resultant, no, that horizontal component of the resultant. So our reaction here, the horizontal reaction here or resistance to sliding, okay, it should be directed to the left. Okay, so this is called horizontal reaction due to sliding because if it will not be supported by a horizontal reaction, this dam, since it will be pushed, okay, to the right, okay, this will govern this force, no, since this is greater than this force directed to the left, no, so this will govern. So if it will not be supported by a horizontal reaction or resistance, since it will be pushed to the right, so it will slide. So it will slide. So we will solve for those items now for this problem. So let's start solving this. So again, we will solve for row 1 and row 2, and also for the horizontal reaction, no, to sliding. Okay, so we will first draw the free body diagram, okay, of this dam. Okay, so this is the dam. So again, it is the ground, okay, that supports this dam. Okay, so as it was mentioned in the problem, the upward ground reaction, it varies from row 1 to row 2. So here, we can analyze this, no? So we can say that our row 2 is greater or it will be greater here, no? So the analysis here is that we know, okay, that the resultant, okay, of this dam, it will be directed downward to the right. Okay, it will be directed to the right. So meaning to say, okay, the portion or the part of this dam that will experience more stress, okay, is the part, okay, at the right side, right? Since this will be directed to the right. So the portion that will be stressed will be at this part, no, at the right side of this dam. So it will be here at this part. It will be the part, okay, of this dam that will experience the most stress. Actually, at this point, no, it will experience the most stress. So the greater intensity, okay, of our ground reaction, which is row 2, no? So we will assume that it is here. It is located here. Since, again, since the resultant for this dam, again, the resultant is downward to the right. Okay, so the right portion of this dam will experience more stress. Okay, so the reaction, okay, it will be greater here, okay, at the right side, no? And this row 1, no, this is less than the row 2, no? And also for the horizontal resistance, so this will be the horizontal resistance or reaction to sliding. So again, this is directed to the left simply because we know that this dam, no, its resultant, it's downward to the right. So since this is to the right, downward to the right, this is directed to the right. So the resistance or the reaction should be directed to the left. So from here, we will start solving. No? So we have here three unknowns, row 1, row 2, and row RB rather. So we will generate three equations here. So the first equation, okay, so here, no, we will draw this first, no. So for this trapezoidal reaction, okay, so we can solve this by resolving this trapezoidal reaction into its equivalent concentrated reaction or concentrated force. Okay, so for this, no, so we will cut or divide our trapezoidal reaction here into two parts. Okay, so we will divide it into two triangles so that we can solve for the concentrated load of each triangular, this triangle shape, no? Okay, so for this first triangle, okay, so its equivalent concentrated load will be just its area. So its area will be 1/2 times its base is actually 18 feet. Okay, and its height is row 1. So the unit for row 1, so this is, since this is intensity of a uniformly varying force, no? So this should be pound per feet. Okay, so that will be the unit for row 1, and again, the base is 18 feet and the height is row 1. Okay, so from here, no, we can solve for this concentrated load. So again, this is just 1/2 row 1 times 18 feet, so that will be 9 row 1. So that will be the value of this concentrated force, no? So this is 9 row 1 and its unit is already pound. So this 9 row 1, its unit is already pound since this is already a concentrated load. Now for this triangle here, so for this triangle, so its area will be 1/2 base. So the side here that will serve as the base will be this. So this is row 2. and its height will be this side, no? So this will be the height, that is 18 feet. Okay, so that is 18 feet. So again, 1/2 rho 2, its unit is pound per feet times 18 feet. So feet will be cancelled, and what will remain here is 9 rho 2. Okay, so this will now be the concentrated load, and this is pound already, 9 rho 2 pound, no? So this is the equivalent concentrated load of this triangle, no? So from here, no, we can now start solving. So we can sum up forces horizontal. So for summation of forces horizontal, we will equate that to 0 since this is equilibrium, and all the forces directed to the right will be positive. So for the first force, that will be 10,000 pound, and it is directed to the right, it will be positive here. For 6,000 pound here, okay, so this F, no, this force F, which is equal to 6,000 pound, this is actually applied perpendicular to this incline. So if we are going to draw a vertical line here, so the angle of this force F from the vertical line here will be 60 degrees as well. Since this is 60 degrees from the horizontal, this incline, no? So it will be 60 degrees from the vertical as well. So from that, no, the vertical, horizontal, no, the horizontal component of this 6,000 pound force, so it will be, we will use sine here, no, so this is, since this is, the angle here is here, so the vertical component of 6,000 pound force will be 6,000 sine 60 degrees, and it is directed to the left, so it will be negative here. And we also have here this horizontal resistance or reaction, so that will be RB, and this is directed to the left, so it will be negative here. So this will be equated to 0. So from here, we can directly solve for RB. So we will just transpose RB since that is negative, no? So if we transpose it to the right, so it will become positive. So the value of RB will just be 1,000 or 10,000. 10,000 minus 6,000 times sine 60. So that will be 4,803.85 pound, no? So now that will already be that is already an answer. Okay, and also we can generate another equation, so that will be summation of moment at B. So for summation of moment at B, the forces that have a moment are force P, this force W, force F, this concentrated force, and this concentrated force as well. RB will have no moment about point B since it will pass through point B, no? So let's start summing this up. So for the first force here, so this concentrated load, again, this is 9 rho 1. So for this 9 rho 1, its moment arm about point B. So as we know, this concentrated load, this is applied, okay, here, no? So this distance, okay, from the tip, no, from the tip of this triangle, from the tip of this triangle to the application or position of this concentrated load, as we know, this is 2/3 L, and the L here is 18 feet, so this will be 2/3 of 18, that will be 12 feet. So that will be the moment arm of this 9 rho 1. So that will be 9 rho 1, okay, times 12, okay, and its rotation about point B will be clockwise, so it will be positive here. Now for our 9 rho 2, okay, so its moment arm will be this perpendicular distance, and as we know, since our concentrated load, no, this is here, no, so as we measure this distance D, no, from the this vertical side of this triangle, no, okay, so as we know, this is 1/3 L. So this will be 1/3 of 18 feet, so that will be 6 feet. So that will be the moment arm of 9 rho 2. Okay, and its rotation about point B will be clockwise, so it will be positive here. Now for this 6,000 pound force, so as we know, this is already a perpendicular distance, no? This has perpendicular distance from point B. So this 4 feet, okay, is the perpendicular distance of this force F, no, about point B. So that will be the moment arm already. So that will be 6,000 times 4, and its rotation about point B will be counterclockwise, so it will be negative here. Now for this 24,000 force, no, so its rotation about point B or moment about point B will be 24,000 times its moment arm, which will be 18 feet. 18 feet minus 7 feet, so that will be 11, okay, and its rotation about point B will be counterclockwise, so it will be negative here. Now, for this 10,000 pound force, so its moment about point B will be 10,000, and its moment arm will be 6 feet. Okay, and its rotation about point B will be clockwise, so it will be positive here. And this will be equal to 0. Okay, so from here, as we can see, we have two unknowns here, rho 1 and rho 2. Okay, so this will be our equation 1. So we have to generate another equation to solve for rho 1 and rho 2, no? So we can also sum up forces vertical, no? So that will be easier instead of summing up moment at A, because if we sum moment at A, so that's also possible, no, to sum up moment at A. But the thing here is that if we sum up moment at A, we will find it difficult to solve for the moment arm of this force F. Okay, so instead of summing up moment at A, okay, we will choose to sum up forces vertical instead. No? So summing up forces vertical, okay, so the vertical forces here are 9 rho 1 upward, so positive. 9 rho 2, this is also upward, so it will also be positive here in our summation. 24,000 is downward, so it will be negative here. And then the vertical component of 6,000 pound force here is 6,000 cosine 60 degrees. Okay, and it is downward, so it will be negative here. So this will now become our equation 2. So from here, we can solve these two equations, okay, to solve for rho 1 and rho 2. Okay, so solving for rho 1, okay, so from equation 2, so rho 1 will be equal to negative 9 rho 2 plus 24,000 plus 6,000 cosine 60 degrees over 9. Okay, so simplifying that, that will be equal to negative 9 or negative rho 2 plus 8,000 over 3 plus 1,000 over 3. So we're going to substitute this rho 2, okay, to our equation 1. Okay, so substituting rho 1 to equation 1, that will become 9 times negative rho 2 plus 8,000 over 3 plus 1,000 over 3 times 12. So this is rho 1. Okay, plus 9 rho 2 times 6 minus 6,000 times 4 minus 24,000 times 11 plus 10,000 times 6 equal to 0. Okay, so simplifying this, so as you can see here, only rho 2 will be the unknown. Okay, so we can solve for rho 2 from here. So simplifying this further, so this will become negative 108 rho 2 plus 288,000 plus 36,000 plus 54 rho 2 minus 24,000 minus 264,000 plus 60,000 is equal to 0. Okay, so we will just combine all rho 2 here. So this rho 2 and rho 2 we will combine, and we will combine all the constants. Okay, so negative 108 rho 2, okay, plus 54, that will be negative 54 rho 2. Okay, and combining the constants, that will be 288,000 minus or plus 36,000 minus 24,000 minus 264,000 plus 60,000. So that will be 96,000, no? So this will be equal to 0. And solving for rho 2, so this will just be, we will just transpose negative 54 rho 2 to the other side so that it will become positive 54 rho 2. So solving for rho 2, that will be 96,000 divided by 54. And that will give us 1,777.78 pound, no, per feet. So take note of the unit, it is pound per feet. Okay, so as we know, okay, our rho 1 is pound per feet. Okay, since this is intensity of a varying force, no? Okay, so this is again for rho 2, that is 1,777.78 pound per feet. Okay, so to solve for rho 1, we will just substitute this rho 2 to our equation, no? So let's say from equation 2, okay, we will just substitute our rho 2 here to solve for rho 1. So substituting rho 2, no, so that will be negative rho 2, which is 1,777.78 plus 8,000 over 3, okay, plus 1,000 over 3. So that will give us 1,222.22 pound per feet. So this will now be the row 1 and row 2. Okay, so this will now be the answers for this sample problem. Okay, so we already solved for the horizontal resistance or RB. Okay, and we already solved for row 1 and row 2. Okay, so let's proceed to sample problem number 4. The uniform rod weighs 420 pounds and has its center of gravity at point G. Determine the tension in the cable and the reactions at the smooth surface at A and B. Okay, so here we have here a rod. Okay, and this rod, it is supported by this smooth surface, no? Here at B, and here also at point A, no? It is also supported by a smooth surface. Okay, and it is mentioned in the problem that the center of gravity of this rod is at point G. So meaning to say we will apply our the given weight, no, which is 420 pound of the rod, okay, here at point G. Okay, but in some instances, if the center of gravity is not given, okay, if the point of center of gravity, okay, is not mentioned in the problem, so automatically the weight, okay, of the body, okay, will be applied in the center of the body. Okay, so but in this case it is given, so we will apply the weight of this rod, okay, at point G. Okay, so the questions here are, we have to determine the tension in the cable. So the cable is this, so we have to determine the tension force that is provided by this cable, and also we have to solve for the reactions at the smooth surface at A. Okay, so we will solve for the normal reaction here, and also for the normal reaction here at B. Okay, so let's start solving this. So we will solve for T, which is the tension force provided by this cable. We will also solve for NA, or the normal reaction at A. Okay, and also for NB, or the normal reaction at B. So of course, for our solution, we have to construct first our free body diagram. So for our free body diagram, you have to apply the weight. So don't forget the given weight. So the given weight is 420 pounds, and it is applied at the center of gravity, no? It is at point G, so it is given in the problem. Okay, so it will be applied here. And also for your cable, no, it will provide a tension force. So this will be the tension force provided by the cable. Okay, of course, this is always pull, no? So this is pull. Okay, so for NA, no, or for here at reaction at A, no, so we will name it as NA. So this is the normal reaction. So it will be applied at the point of contact of the rod and the surface, and it will be applied perpendicular to the surface. Okay, so this will be NA. So here at point B, no, so the normal reaction here, okay, will be applied at the point of contact of this surface and the rod, no. So since the surface here actually is just a corner, okay, so this corner, no, this rod is leaning on this corner, no, so we will apply our NB perpendicular, no, to the rod, okay, to the inclination of this rod. So it will be applied this way. So if this is 45 degrees here, now if we draw a vertical line here, so NB will also be 45 degrees from the vertical. Okay, so from here, we can now solve, no, using three equations. So this is three unknowns, no, we have three unknowns here, so we can solve this using three equations. So we can use summation of forces horizontal, summation of forces vertical, summation of moment, no. So it depends on us if we will use two summation of moment and then one summation of forces, or two summation of forces and then one summation of moment. So for this, no, we will sum up moment at B. Okay, so point B is here, so we can take moment here at point B. So NB will have no moment since it will pass through point B. Okay, so let's start summing up moment. So it will be equal to 0, and clockwise rotations will be positive. Okay, so for NA, so the moment of NA about point B, so NA times its moment arm, which is 8 feet. So that will be NA times 8. Okay, and it will rotate about point B counterclockwise, clockwise. So it will be positive here. Now for T, so this is T. Okay, so for this reaction or tension force T, so its moment about point B will be T times its moment arm, which is 4 plus 2. So that will be 6. And its rotation about point B will be counterclockwise, so it will be negative here. Now for our 420 pound 420 pound weight, no? So its moment about point B will be 420 times its moment arm. Now for its moment arm, okay, so this is its moment arm. Okay, so we solve for this moment arm. So this is not given, no, in the illustration. So we can solve for this moment arm by using this side, no? This is 2. And we know that the angle here is the same as the angle here. Okay, so if this is 45, this is also 45 degrees. So using this side of the triangle, which is 2 and 45 degrees, okay, so we have, if we want to solve for this, this is the adjacent side of this triangle. Okay, so this will be the triangle form. The angle is 45 degrees and the opposite side is 2. So if we solve for the adjacent side, we can use tangent. So tangent 45 degrees equal to TOA yun, no? So that is TOA, opposite over adjacent. So tangent 45 degrees equal to 2 over adjacent, which is the unknown. So solving for the adjacent, that will just be 2 over tangent of 45, which is also equal to 2. Okay, so this side, no, this is also 2. So that will become the moment arm of our 420 pound force. So that will be 420 times 2, and its rotation about point B is counterclockwise. So it will be negative here. So this will be equal to 0. So this will become our equation 1. So we have to generate more equations since we have two unknowns here, NA and T. So we cannot solve directly for any of these unknowns, no? So we can sum up forces vertical also. So summing up forces vertical is equal to 0. So positive for upward forces. So NA will be positive. 420 will be negative. Okay, and the vertical component of NB will just be NB cosine. No? Cosine 45 degrees equal to 0. So this will be our equation 2. Okay, so we cannot solve equation 1 and equation 2 simultaneously because they have different unknowns, no? So we have to generate one more equation. So we can use summation of forces horizontal is equal to 0. Okay, so positive for forces directed to the right. Okay, so the forces that has, or the horizontal forces here, okay, are tension. Okay, that is positive. And then we have here the horizontal component of NB. So the horizontal component of NB is NB sine 45 degrees, and it is directed to the left. So it will be negative here. So this will be equal to 0. So this will become our equation 3. Okay, so from these equations, no, so we can analyze this, no. So from equation 2, okay, we can actually solve for NA. Okay, so in terms of NB, okay, and also for from equation 3, okay, we can solve for T, okay, in terms of NB. Okay, so this NA, okay, we can substitute this to equation 1, and this T, okay, we can substitute it to the T here in equation 1. Okay, so the unknowns here will become NB, no? So we will just think, no, if we are solving this, no, we will think of a way, okay, where we can express the unknowns, okay, in the equation. Okay, we have to express both unknowns, okay, into a common unknown. So in this case, we will we will express NA in terms of NB, okay, and also we will express T in terms of NB, which we generated, no, from equation 2 and equation 3. So we will just substitute them to equation 1 to solve for NB. Okay, so substituting NA and T to equation 1. So NA from equation 2 and T from equation 3. So we will substitute that in equation 1. Okay, so our NA here from equation 2 is 420 minus NB cosine 45 degrees times 8 minus T. So our T from equation 3 is NB sine 45 degrees, okay, times 6 minus 420 times 2 is equal to 0. Okay, so for here, no, so the only unknown is NB. So we can simplify this further. Okay, so 420 times 8, that will be 3,360. And then NB cosine 45 degrees or negative NB cosine 45 degrees times 8. That will be negative 4 square root of 2 NB. And then we have here NB sine 45 degrees times 6. That will be, so this is negative here, negative 3 square root of 2 NB. And we have here negative 420 times 2. That will be negative 840 is equal to 0. So simplifying this further, we just combine all the NB, okay, and all the constants. So negative 4 times square root of 2nb minus 3 square root of 2nb, that will be negative 7 square root of 2nb. And 3,360 minus 840, that will be positive 2,520. So this will be equal to 0. So solving for nb, we just transpose this to the other side so that it will become positive 7 square root of 2nb. And solving for nb, okay, so that will just be 2,520 divided by 7 times square root of 2. So that will be 254.56 pounds. So that will now be the value of NB. Okay, so solving for NA, we just substitute this obtained NB, no, to this equation from equation 2. Okay, so we just substitute it here. So this will be 420 minus 254.56. So it's better if you input all the obtain decimal places for NB, no, while computing for NA. So times cosine 45 degrees. So that will give us 240 pound. Okay, so that will be the value of NA. To solve now for tension force T, okay, so we will also substitute NB here. So our NB again is 254. Okay, 254.56. Okay, so again, it's better if you include all the decimal places. Times sine 45. Okay, so that will be 180 pound. Okay, so this will now be the answers for this problem. We have already solved for T, for NA, and NB. So we can now box these answers. Okay, for sample problem number 5, a pulley 4 feet in diameter and supporting a load 200 pound is mounted at B on a horizontal beam as shown. The beam is supported by a hinge at A and rollers at C. Neglecting the weight of the beam, determine the reactions at A and C. Okay, so as we can see here in the problem, now we have here a pulley. So this is the pulley. Okay, so this supports a 200-pound load. And this 200-pound load, this is actually attached, no, by this cable, no. So this cable, no, this is supported, no, by this pulley. Okay, and this pulley is actually mounted at point B on a horizontal beam, no. So this is attached, no. This pulley is attached to this beam, okay, by a pin, no, here at point B. So this is pin connected here. Okay, so the beam, no, this is the beam. Okay, so this beam is supported by a hinge at A. So this is the hinge at A and a roller at C. So neglecting the weight of the beam, no, we will determine the reaction at A. So this is our point A, and this is point C. So we will solve for the reactions at those points, no. And also from this problem, the weight of the pulley is not mentioned. So meaning to say we will neglect, okay, the weight, okay, or the self weight of the pulley here. Okay, so we will start solving this. So we will solve this, no? So again, we will solve for the reaction at A and reaction at C. Okay, so for reaction at A, take note, okay, that the question in the problem is reaction at A and reaction at C. Okay, so the question is not the components of the reaction. So in this case, no, as we know, at point A, no, so this is hinge support, so it will have horizontal and vertical reaction. Okay, so those horizontal and vertical reactions are just components of the reaction at A. So if we solve for the horizontal and vertical reaction, we have to solve also for the resultant of those two components, no, to solve for the reaction at A. So here at C, we have no problem here since there will only be one reaction here, which is an upward vertical vertical reaction, no? So that will be the reaction at C, no? So to solve this, of course, we have to construct first the free body diagram. So we will construct the free body diagram of the entire structure. Okay, so if we construct the free body diagram of the entire structure, we will show here the weights, no, the weights which is not given, no. So for pulley, no, it's not given, so we will assume the weight of the pulley, no, as 0, no. So we will assume this as weightless. And also it's mentioned in the problem that the weight of the beam, no, is also 0. So assuming weightless, no, it was mentioned in the problem. So there will be no weight for the beam and the pulley, no. And this pulley, okay, it is supporting this 200-pound load, no. So this is the 200-pound load. Okay, so we will now uh, provide here, no, the reaction forces, no. So for this structure, no, for the FBD of the entire structure, we will show here the reactions of the main support. So in this case, the main supports are point A, hinge at point A, roller at point C, and this cable, no. So since this is the support, no, the support for this 200-pound load, so this will also be a main support, no. So here at this pulley, no, so this 200-pound, this is placed here or supported by this pulley. So this is a cable, no. So as we have discussed from our discussion in frictionless pulley system, okay, if we have a cable, no, let's say with a force, no, so this is 200-pound, no, along the continuity, okay, of that cable, okay, if it is supported by a pulley, a frictionless pulley, no, along the continuity of that cable, that force will be constant. So if this is 200-pound, okay, and this is supported by a cable, no, supported by this frictionless pulley, no, so along its continuity, along the continuity of this cable, if this is 200 pounds, so this will also be 200 pounds. So this will be tension, okay, so since this is a cable, so this will also be 200 pounds. Okay, so for our reaction at A, no, so this is a hinge, so it will provide a horizontal and vertical reaction, so we will name it as AH and AV. So for roller at point C, so it will provide a vertical reaction, so we will name it as RC. So it will be applied perpendicular to the surface, no, where the roller is lying, no. So from here, okay, as we can see here, we have here three unknowns, so we can generate three equations. But the problem here is if we use moment equation here, okay, so it will be difficult, okay, to solve for the moment arm of this 200-pound force about point A. So it has no given perpendicular distance, no, from point A to 200-pound force, no. And also if we resolve our 200-pound force into its horizontal or vertical component, let's say we put the horizontal or vertical component here. So from the figure, there is no given dimension here, no, for the distance from this point to point A, no. So there's no distance. So it will be difficult. And also if we resolve the component of this 100-pound force somewhere here at this point, no, for the horizontal component of that reaction force, no, or of that 200-pound force, so it will just be the radius of this pulley, no. But the problem is the vertical component, so it will be difficult to solve for the moment arm of that force about point A, no. So instead of solving this, no, using the free body diagram of the entire structure, okay, we will instead construct the free body diagram of each body. Okay, we will construct the free body diagram of the pulley, okay, of this pulley and of the beam separately, no. So for the free body diagram of the pulley, so as we can see here, this pulley is actually supported here at at point B, no, by a pin. So this is attached or pin connected here. So it is connected to the beam, no, by this pin. So since this is a pin, as we know, pin provides two reaction forces. So that is horizontal and vertical reaction. So the direction of the horizontal and vertical reaction, we will depend that, okay, on the forces that we have here. So as we know, the forces here are 200 pound, this 200 pound downward, and this 200 pound inclined 60 degrees, no, from the vertical. Okay, so for our BH, so as we can see here, the only force that has horizontal component here is this 200-pound force, no? So it is directed to the left. So of course, the reaction here should be directed to the right to keep the equilibrium of the system. Okay, and for BV, we are not so sure here because we have here 200 pound and this is 200 pound, no? So we don't know which will govern here. Okay, if what will be the greater force here, no? But in this case, we will assume that BV is upward, no? So from here, okay, so we can use two equations here since we have here two unknowns, BH and BV. So only two equations are needed. So we can use summation of forces horizontal is equal to 0 and summation of forces vertical is equal to 0. So I think no need to use for moment equation here, no? So since we will find it difficult nga, no, to solve for the moment arm of this but actually, if we sum up moment here at B, okay, we can know the perpendicular distance of 200 pounds since this no, we don't know, no, we don't know the moment arm because the radius is not the perpendicular distance here. Okay, it's not ano, no? Okay, so we cannot do that pala, no? We can use summation of moment here, ha? And also, if we use summation of moment here at point B, BH and BB will be cancelled. So I just want you to realize that. And if that's cancelled, no, there will be no unknown quantity that we can solve. Okay, so we will know, it will not be necessary, no, to use moment equation here. No, so we will not need that equation. Okay, okay, so from here, no, summation of forces horizontal is equal to 0. Um, Forces directed to the right will be positive. Okay, so BH will be positive. 200 pound, no, its horizontal component will be 200 sine 60 degrees. Okay, so that will be negative since it is directed to the left, and it will be equal to 0. So for our BH, okay, for our BH, if we solve that, we just transpose negative 200 sine 60 degrees to the other side. So that will be 200 sine 60. Okay, so that will be 173.21 pounds. So that will be the value or the answer for BH, no? So this BH, okay? So we are not asked to solve for BH, ha, or for the reaction at B. So no need to box this, ha. Okay, so we can solve also for BV. Okay, so solving for BV, okay, summation of forces vertical. Okay, so the forces here that have a vertical component or vertical, no, are BV, and this is upward, so it will be positive. 200 will be negative since it is downward, and the vertical component of this 200-pound force is 200 cosine 60 degrees. Okay, so this will be equal to 0, so we can solve here for BV. So for our BV, so that will just be, we will just transpose negative 200 plus 200 cosine 60 degrees to the other side, so that will become 200 minus 200 cosine 60 degrees. So that will be 100 pounds. So this will now be the BV. So the reason why we solve for BH and BV here, because if we construct the free body diagram, okay, the free body diagram of um, the beam here. So this is our beam. Okay, so if we construct its free body diagram, the force, okay, or the reaction force here at point B from the free body diagram of the pulley, this BH and BV, it will be transferred. Okay, it will be transferred to the free body diagram here at free body diagram of the beam. no, since they are connected here at point B, no, they are pin connected here. Okay, so from here, no, as we know, if we transfer BH and BV to the free body diagram of this beam, so it will be directed oppositely. So if BV here is directed upward, here it will be directed downward. And if BH is directed to the left here, if we transfer it, it will be directed to the left. So from here, no, so we can solve for the free body diagram here of this beam, and we can solve for AH and AV and for the reaction at C. So let's start solving that. Okay, so solving for the reactions at A and reaction at C, so three unknowns, we can use three equations, no? Summation of forces vertical, summation of forces horizontal, and one summation of moment. No? So we can also use two summation of moments and one summation of forces. So it depends on your choice. No? So in this case, we will use summation of forces horizontal to solve for AH. No? As we know, we already solved for BH, no? From our previous solution, no? So solving for AH, so solving for summation of forces horizontal, that will just be AH minus BH, which is equal to 173.21. So that will be negative since it is directed to the left here, and this will be equal to 0. So solving for AH, that will just be 173.21 pound. So this is not yet answer, no, an answer for this problem. So this is a component of the reaction at A. So what we need here is reaction at A. So we need to solve first for AV, also to solve for RA, ha, okay? So to solve for the AV, no, for AV, so we will sum up moment at point C. Okay, so summing up moment at point C. Okay, so RC will be cancelled, and the unknown force here that will have moment will only be AV. Since AH will also pass through point C, no? So AH will also be cancelled. So solving for the moment about point C, so AV, its moment will be AV times moment arm, which is 4 plus 4, that will be 8, and it will rotate clockwise, no, about point C, so that will be positive here. And for BV here, so as we know, the value of BV is 100, and its moment about point C will be BV times 4. So this is 4. Okay, so its moment rotation, or the direction, will be counterclockwise, so it will be negative here. So it will be equal to 0. So the only unknown here is AV, so we can solve for AV. So that will just be, we transpose negative 100 times 4 to the other side. That will become positive 100 times 4 divided by 8 to solve for AV. So 50 pound. Okay, so this will now be our AV. So we can now solve for the reaction at A by solving for the resultant of AH and AV. So that will just be square root of AH squared plus AV squared. So our RA here will be square root of 173.21 squared. So it's better if you input all the decimal places here, no, that we obtain from AH and AV, plus 50 squared. So that will give us 180.28 pound, no? So this will now be the reaction at A. So we will also solve for the reaction at C. So as we know, this is just a vertical reaction here, no? So we already solved for AV, so we can use summation of forces vertical to solve for RC since we already solved for AV. So summation of forces vertical, it will just be AV minus 100 plus RC is equal to 0. Okay, so RC here is the unknown, so AV is 50, so we just substitute AV here. So this will be 50 minus 100 plus RC. So solving for RC, that will just be positive 100 since we will transpose it, minus 50. So that will be 50 pound as well. No? So RC, or the reaction at C, will just be equal to 50 pounds. So this will now be the answers for this problem. RA is 180.28 pound and RC is 50 pound. So this will now be the answers. So that concludes our discussion about this topic. So I hope that you learn, and I hope that you attain the learning outcomes for this topic. And see to it that you answer the assessment task assigned for this topic. And you have to submit that on our next meeting. So happy studying, class. God bless you and keep safe. Bye-bye.